Can you do an analysis of the Area 51 earthquakes? I've gotten a lot of these comments lately. Can we talk about it? Sure, absolutely. I'm always happy to talk about earthquakes, although this is like the most boring earthquake sequence in the world, but we can talk about it. So, first, I'm Dr. Wendy Bohan. I have a master's degree and a PhD in earthquake geology. I've been working in this field for more than 25 years. So, in this video, I want to answer two main questions. The first is it unusual to have earthquakes in this area? And the second question is, are these actually earthquakes? Since that seems to get to the root of what all of these conspiracy theories are talking about. So, is this an unusual place to have earthquakes? Nope. Nevada has lots of earthquakes, so the crust in this area is undergoing extension. It's stretching that causes faults to form and earthquakes to happen. Now, this is a map showing earthquakes across Nevada in the last year. There are a lot of them. Now, the earthquakes that are happening in Area 51, what about those? So here's a map showing those earthquakes. There was a magnitude 4.4, which is an average size earthquake in Nevada, and it was followed by some aftershocks. That's how earthquakes work. If you go back to my previous videos, you'll see that after just about every earthquake, I say, this is perfectly normal. Aftershocks will happen. They are normal and expected. That is also the case here. So this is just a normal earthquake sequence. It's actually a very boring earthquake sequence. It's well behaved. There's actually a far more interesting earthquake sequence happening up in the northern part of Nevada, but nobody wants to talk about that because there's no conspiracy theory there. It's just interesting science. So anyway, are these actually earthquakes? Yes. And how do we know? This is a really interesting question, actually. There are lots of different things that put energy into the ground and they cause the ground to shake. That ground shaking is recorded by seismic instruments called seismometers. So all of these different things put energy into the ground and they make different patterns. They look different on the seismic recording. So here's an example of what a landslide looks like. Now here's an example of an elk walking near a seismometer. Your footsteps can also be picked up by seismometers if you're close enough. But the question most people are interested in, I'm guessing, is how do we know if this is like a bomb or something like that? And so that has to do with the ratio of waves that an earthquake produces versus what a bomb produces. They both produce waves called P waves and S waves. So in a bomb, that's a point source explosion, right? And it creates strong P waves and weak S waves. An earthquake is a rupture along a fault that creates weak P waves and strong S waves. So this is a comparison showing the shape of a seismic recording of an earthquake and of a bomb. And you can see that they look different. So anyway, I'm going to include a video at the end of this. It's from IRIS, now that's called EarthScope. It goes into more detail about how we tell the difference between different types of things, especially earthquakes and bombs. So if you're interested, you can check that out. But in closing, these earthquakes are just earthquakes. They're normal earthquakes. They're actually kind of boring earthquakes. So can we talk about something more interesting now?
Seismometers can detect anything that shakes the ground, from earthquakes to industrial noise to bombs. But how do seismologists tell the difference between, say, an earthquake and a large bomb exploding when both release intense ground-shaking forces? Let's examine two methods that are used. The first will introduce compressive and extensional effects of seismic waves as they are reflected in focal mechanisms, and the second will show actual seismograms. When a bomb detonates, the concussive effect pushes seismic energy in the form of compressional P waves, similar to sound waves, in all directions away from the point source. Let's watch it in map view using springs to show the compressions. When the P waves reach each of the seismometers, they record an up signal because the ground is bumped up as compressional first motions. An earthquake doesn't explode from a point, but by sideways slip on a fault plane. When the fault slips, it both pushes the rock ahead with a compressional force and pulls on the rock behind, resulting in an extensional force. Let's replay it using springs to show these compressions and extensions. The part of the fault moving towards the sensor causes a compressional first motion, and the part of the fault moving away from the sensor causes an extensional first motion, recorded as a down on the seismogram. This process means that seismic stations record both extensional and compressional P waves. If we represent compression with plus signs and extension with minus signs, we see that 2 quadrants are compressive and 2 are extensional. If we darken the compressive quadrants, a distinctive pattern called a focal mechanism arises. This pattern tells us that there was a horizontal strike-slip motion on this fault. A variety of patterns indicate whether the fault was normal, reverse, strike-slip, or a combination. In the case of the bomb, all regions of the pattern have pluses. Thus, it would be black in all quadrants. Distinguishing an earthquake from a bomb also requires a close examination of seismic wave patterns. We can show the difference between them by using pairs of seismograms from earthquakes and nuclear explosions that occur near each other. Because the seismic energy of an explosion pushes outward equally in all directions, the result is strong P waves and weak S waves. In contrast, the rapid sideways motion of an earthquake typically produces weak P waves, and because of that shearing motion, it generates strong S waves and surface waves that are of higher amplitude and slower, thus they show up later. In summary, the two principal methods to discriminate between an explosion and an earthquake are by using their seismograms and by their focal mechanism.